Okay, my name's Andrew McCarthy. I'm a postgraduate researcher at the Computer Science Research Centre at the University of the West of England in Bristol. My research interests are in cybersecurity and in machine learning. And so I'm going to talk today a little bit about my recent paper, Feature Vulnerability and Robustness Assessment against Adversarial Machine Learning Attacks. So if I could have the next slide. And yeah, so if I just set the stage with this problem description, human and computers see things in different ways. So computers see everything as numbers. They're really good at dealing with numbers, and in a large extent, dealing with numbers is what computers do. That's all they do. But human perception is a bit more permissive. So people easily overlook minor changes in pixel size and color, whereas computers can easily distinguish between millions of individual colors. And the most famous sort of example that I can think of this is this panda that is classified by a machine learning system as a panda with fairly high confidence, around 60% confident that it's a panda. And then if we add adversarial noise shown by this epsilon value here, then we create an adversarial example. And then what that means is that suddenly the same classifier now considers that this image is that of a gibbon, and it believes so with high confidence. So it's nearly 100% certain that it's a gibbon. And so if, yeah, the next slide. So how do we go about creating this this noise, this carefully crafted noise? So one of the simplest ways of doing it is through fast gradient descent. And this is where we are able to minimize the loss function that's so critical in machine learning by using an iterative algorithm to descend the gradient. So basically, we start with an initial weight here at the top, and then through a sequence of steps, we descend the gradient, or if you want to be more precise and mathematical, the inverse gradient. So as you step down the gradient, you will come to a local minimum or a global minimum even for the loss function. So FGSM, as its name suggests, is fast rather than optimal, and it results in minimal perturbations, so really small, almost imperceptible perturbations. And their gradient is used to decide whether to increase or decrease each feature that allows us to minimize this loss function. And then all the features are shifted simultaneously. And then the next slide. So why is this important? I mean, I think the implications in image recognition is clear. If you can fool a classifier into thinking an image of a panda is that of a gibbon, then that's far from ideal. There's other applications in non-visual domains where this is also applicable. So for example, we're using machine learning classifiers now to discriminate between benign and malicious traffic in network intrusion detection. So this research helps to better understand the weaknesses in machine learning systems, improve the robustness of neural networks, and help to retain acceptable classification accuracy. And then another reason why this is important is that cyber warfare, cyber espionage, cyber crime is endemic. So you've got cyber criminals who are using ransomware to claim ransoms from high impact targets. You've got nation states looking for advantages against other nation states. Our defenses for this are machine learning systems that are able to discriminate between benign or malicious traffic. And the problem is that the bad guys, they're always looking for a way to evade our defenses. And currently, adversarial examples are kind of like the chink in our armor. They're our biggest weakness at the moment. And we've seen this in ransomware attacks such as WannaCry, and then with the SolarWinds attack as well, kind of shows how reliant we are on intrusion detection systems. So if I could go to the next slide. And so our related work section kind of covers 4 distinct areas: adversarial attacks, architectural defenses, feature selection, and visual analytics. So Ayub et al. Used JSMA, or Jacobian Saliency Map attack, to evade network defenses. Wang et al. Used defensive dropout as a way to defend against adversarial examples. Hamed et al. Used feature selection as a way of improving accuracy, and he used recursive feature addition. And then Legg et al. In the realm of visual analytics used visual analytics to assess the robustness of classifier performance using a tool called Activate. So if I could go to the next slide. And so most previous work in this sort of domain has focused on the impact of adversarial examples, or aims to improve the accuracy under normal conditions. And sometimes they're using feature selection, and most often they're looking in the visual domain. So we address the problem of improving the robustness of machine learning models against adversarial attacks. We use feature selection, and we've chosen to use an intrusion detection system case study for that. So we explore the risks of implementing machine learning intrusion detection systems. We again focus on improving the robustness rather than the accuracy. And we're using a fairly recent data set from the Canadian Institute for Cybersecurity. And we're kind of focused most on the distributed denial of service element of that in this research. And so the next slide. And so the advantages of using this data set, we've got a mixture of benign traffic and some common attacks in there. It resembles true real world data. So the actual packets going across the network, we've got packet captures or PCAP files. Those PCAPs have been converted and analyzed using the SIC flow meter tool into network flows. And then those flows have been labeled using the timestamp, source and destination IP, source and destination ports, and the protocols. And then, as I said, they've been labeled with the attack types. Another advantage we get from this data set is because it's been collated in a working lab, we've kind of got a realistic background traffic as well. And there's approximately 5 days worth of traffic with a selection of common attacks there. What we're most interested in is the distributed denial of service there. So the next slide. So if I pick out some of the key features from the research, we started off with the feature analysis, where we extracted the features and tried to categorize the traffic as either benign or malicious. We went through dimensionality reduction. So we used a range of dimensionality reduction algorithms, so principal component analysis, T-distributed stochastic neighbor embedding, uniform map and projection. But the important thing, rather than their names, is that what we found is no single cluster for malicious traffic. And if you look at the image in the right there, you can see the malicious traffic in dark blue. And we're beginning to see the starts of some clusters there, but what you'll notice is there isn't a single cluster for malicious traffic, and actually it's also spread quite across a large portion of the benign space as well. And so from that feature analysis, we thought we'd also look at the raw features. And one of the things we thought was that for distributed denial of service traffic, the time between packets arriving is going to be key for looking at the and discriminating against benign and the denial of service traffic. So we were looking at the inter-arrival time, and we've plotted those as parallel coordinates, which I'll show you the plot shortly. But if I could have the next slide. And then, so moving on from the analysis phase, what we did was we built a binary classifier model as a baseline. So we were able to discriminate between benign and distributed denial of service. We've used shuffled stratified k-fold to reduce our sample bias. K here is 5. And then what we found from the baseline classifier is that we're getting really, really high accuracy results from that. So the next step was then to generate FGSM adversarial examples from the DDoS samples. So here we're taking the DDoS samples, trying to make them look like the benign traffic by using FGSM. And what we saw from that is a significant reduction in the accuracy from our baseline model. And so then to improve upon this situation, where we've got the model, but we've reduced its accuracy, we've looked at recursive feature elimination, and we assessed the perturbation to each of the features, and then remove the feature with the largest perturbation, and then retrain the model with that feature missing until we got to an optimum feature set that was optimized for accuracy. And so this is some of the results that we saw. I promise you the plot on the inter-arrival time features. And so what we see here is that we were looking to see if we could make the denial of service traffic to appear benign. And what we've seen here is that the adversarial examples fit quite well within the benign traffic, and the values seem to fit quite well, and it's kind of difficult to actually pull them apart. So if we go to the next slide. So the results on the feature elimination side of the research, for different values of epsilon, so the perturbation size, so small, medium, and large, what the plots show is that for the small perturbation sizes, a feature set of around 60 features is enough to mitigate against the effects of FGSM. For medium-sized perturbations, a feature set of 20 is enough to mitigate against the effects of FGSM. But for the large perturbation sizes, a feature set of 20 is insufficient to completely mitigate against the effects of FGSM. But we got quite close to the original accuracy here at the top, on the right-hand side of the slide. And so if I go to the next slide, the good news here is that what we have seen is a trajectory to bigger perturbations. So as we've reduced the number of features, we've forced the perturbation size to be larger. And the hope here is that these larger perturbations will become more evident to network analysts, and they'll be able to more readily identify this traffic as malicious or adversarial in nature. So the next slide. So to summarize, what we've got is a generalizable approach for assessing the vulnerability and robustness of our features, a suitable methodology for assessing the susceptibility of features to perturbation attacks. We've also got a systematic way to remove those vulnerable features to maintain the acceptable classification accuracy, which is key, but also whilst eliminating the features that might introduce more subtle attack vectors. And then we've also successfully used the feature selection to achieve improved accuracy under FGSM attack. So the next slide. So the direction of this research now goes more towards the constraints of the network traffic domain. So thinking about network intrusion attacks, there's certain features that can't change. So the simplest ones I can think of are destination IP address, destination port. If those change, then the attack is ineffective. There's also a problem that firewalls might recognize some of these packets as malformed and will just drop them. So there's some constraints there that we need to think about for the network traffic domain. So what I'm going to be looking at is different types of attack other than FGSM. So I'm thinking about other areas such as the Jacobian saliency map attack that doesn't require to change all the features in the sample. And so that might be one way of getting closer to an attack that will work and not be dropped by firewalls and will be effective. I'm also going to be looking at considering whether our model is overfitting. So we have seen really high accuracy rates, which can be a sign that the model is overfitting. We need to do some work on that to determine whether that is happening and why that's happening. There's some ideas that we might be looking at the way that we're splitting the train and test data might be causing us problems there. But as I said, I need to do some more work there to recognize whether that's actually happening. And then further on, I'm going to be looking at ensemble classifiers, using multiple classifiers to see if there's any advantage to robustness from using multiple classifiers and whether they'll give different results. Also looking at the transferability of adversarial examples and see whether I can transfer adversarial examples from one model to another. And then I'll also be moving, this is a binary classification problem at the moment, and I'll move that into the multi-class and use some of the other classes. So if we think about, just leave you with a few words really. So basically the number of features can be used as an attack surface, and we can reduce that attack surface by reducing the number of features. But if we're careful about how we select those features and which features we keep, we can reduce the attack surface, but also maintain the acceptable classification accuracy. And then the smaller number of features forces larger perturbations, which hopefully are more readily identifiable as malicious to the network analysts. And yeah, thank you. That's my Twitter handle if you'd like to follow me. But if you've any questions now, I'll take them.
Thanks, Andy. That was really good. I enjoyed it. I learned quite a bit from your FGSM. I don't think I've come across it. That's really good. You've got some questions here, so see how far we go. Okay. So what was the decision making in choosing 5-fold validation as against, say, 10-fold validation? Would you think it would have resulted in a higher level of accuracy or a higher level of expandability in your model?
So really, the thought behind it was to sort of balance the bias that we were getting against long execution times. So it was kind of a balance between running the model for a long time, which was becoming problematic, and actually getting something that we thought would reduce our bias sufficiently.
Thanks, Andy. Another one says, thank you for this insightful presentation. What would you change in the proposed pipeline to deal with multi-class IDS? You did touch about that in your future work about multiple variants and multiple of binary. Is that?
Yeah. So I suppose I think to attack the multi-class problem, I'm looking at the moment. I'm looking at long short-term memory classifiers that might help there with the multi-class problem. Yeah, I think that's the area that I'm looking at the moment. Yeah, I think also there's one issue there that I've got in the data set that I've got, it's kind of imbalanced. So we've got some multi-class, but we've got some classes of attack that we've only got a few samples for, and we've got other classes of attack that we've got lots of samples for, and actually changing the balance there is one of the things that I'm going to have to change going forward.
Okay. Another question is common. I'll try and read it, see if it makes sense to you. It says, within your observations, have you encountered the bow tie, quote unquote, style data scraping attack in which each request is from a unique IP and a user agent and targeted at a unique URL, as this style of attack cannot be defended against using conventional CDN, content delivery network, or WAF countermeasures?
No, I haven't come across that, but I'll certainly make a note and look into that.
Cool.
Thank you.
All right, the one final one before you go is, in terms of moving forwards, are you considering, when you go into other types of attack apart from the FGSM, are you going to compare these initial results from FGSM to the other types of attack types they're going to investigate in future?
Yeah, I mean, I think potentially, I think one of the issues with the FGSM that makes it not really suitable for the intrusion detection systems going forward is that it does require you to change every feature. So I think as a baseline, certainly it's good to compare against. But yeah, I think there are other more constraint-based algorithms that I'll be focusing on in future.
Okay, one last one for myself. So would you consider your work to be used for defensive or for offensive? Because you can use it either way. From what I'm hearing, you can interplay this noise to masquerade and then fool the detector so that the IDS wouldn't classify it as malicious or malignant, and then it goes there to cause havoc. Or would you want to use it as a defensive then to train the actual IDS within an enterprise so that they are versatile in detecting some of these adversarial overlaid noise type of attacks?
I mean, I think it's not either or. I think we can use both. I think one of the issues about using adversarial examples and putting those into our adversarial training is that I don't think it actually solves the problem, because you can then just attack the same classifier and find another adversarial example that reduces loss function with that extra training and with that extra adversarial training data. So yeah, I mean, I think it's not either or. I think, you know, sometimes adversarial training is useful, but I think it's not a panacea really. And so I think, yeah, mostly I'm going to be looking at sort of anomaly detection, I think, going forward.
Would you consider seeing this applied in deception mechanisms? So where you use it to then deceive an attacker into luring them into something like a honeypot type approach?
So I'll see if I've got the question right there. So I've seen sort of deep fakes and these sorts of things. And we've got classifiers now that are able to determine and discriminate deep fakes from actual footage, whereas the humans can't. But if we're able to then fool the classifiers using adversarial examples, we're back to square one again. So yeah, I mean, I think it can be used in a range of different areas.
Thank you very much, Andy.
Okay.
That's all we can take for now. Guys, the fireside chat starts at 3 p.m. UK time. That's the next hour with Professor Ross Anderson of Cambridge University. Come prepared with your questions, and it's going to be interactive, so you can post whatever you want. There is no PowerPoint, no share. It's just a fireside chat with Professor Ross Anderson. See you at 3 p.m. today.
Fabulous.
Thanks,
Thank
Andy.
you, sir.
Thanks, guys. Speak soon.